One of the first key steps in our project was to gain control of the Dobot. We started with a library from GitHub called PyDobot, which communicates with the serial interface of the Dobot. And we had made some modifications of it. For instance, we added a method to turn the air pump on and off, which allowed us to pick up a ducky. We also made a key change, which is that we check the angles requested before we send them to the Dobot. This is important because if you send angles that are outside the range of motion of the Dobot, it will try to get there and it can get stuck and cause a lot of strain on the stepper motors. So we used our kinematics model to verify that the angles were reachable before sending them. Another key piece to controlling the Dobot is the forward and inverse kinematics, which allows us to map from joint angles to the position of the Dobot's end effector and vice versa. The Dobot has a decoupled architecture so that the end effector is always pointing down regardless of its pose. The slide shows our kinematic model of the Dobot. And using some trigonometry and algebra, we were able to derive equations for the end effector position as a function of the joint angles. The inverse kinematics can similarly be derived in a direct manner using the law of cosines. We initially validated our kinematics code by calculating out a few points manually and then checking them with the forward kinematics. We then tested the inverse kinematics by making sure that they mapped the result of the forward kinematics back to the original joint angles. Once we had serial control of the Dobot, we performed some experiments to test our kinematics model. In our experimental setup, we put a piece of graph paper in front of the Dobot and aligned it so that we knew the exact relative distance between points on the piece of graph paper. Then we manually steered the Dobot to each point in the graph paper and recorded the joint angles. We used the forward kinematics model to then predict the position of the end effector and compared it to what we knew it should be from the graph paper. The plot on the slide shows the agreement between the position from the graph paper and the position predicted from the kinematics model. And as you can see, they're accurate to within just a few millimeters. The Dobot has built-in trajectory generation, so if we have some desired angles we want to move to, we just send them and it will figure out the trajectory to get there. However, if we want to do more advanced trajectory planning, such as path planning with collision avoidance, we need to do something else. And we implemented a probabilistic roadmap for this purpose. The probabilistic roadmap works in two steps. So in the first step, we generate it. And this entails randomly sampling the configuration space or the joint angles of the Dobot and checking whether they result in collisions in a model. So we have a model of the Dobot arm, which is a series of triangle meshes, and then we also have some model of the known obstacles in the environment. And we can do triangle-triangle intersection tests to determine whether the Dobot is colliding with any of those obstacles. So then we take the configurations that we randomly generated that aren't colliding and we try to link them up. So the roadmap will test a bunch of configurations in between those 2 points, and if none of them are in collision, then it knows that it can safely move from one to the other. This results in a graph structure where we have nodes at each of these configurations and edges indicating collision-free paths. This can be searched with algorithms such as Dijkstra's graph search. The result is a sequence of trajectories, which we can send to the Dobot and have it follow, as illustrated in this video. As opposed to more local planning methods such as a potential field, the probabilistic roadmap has the advantage that it can find paths around fairly difficult obstacles. So in the video, the Dobot has to take a very circuitous route to get around the wall. It has to actually move kind of out of its way, farther away from the target point before it moves back to achieve its goal.
We use a Logitech C270 webcam to detect and locate objects in the workspace. The webcam is mounted to the end effector of the robot so that it points to the workspace floor. Video processing is achieved using the OpenCV module, and obstacles are tagged with AR tags to simplify being able to detect and locate them. The webcam is calibrated using Caltech's camera calibration toolbox from MATLAB. Following the procedures of this toolbox, we use the C270 webcam to collect 12 images of a checkerboard pattern displayed on a laptop screen. The MATLAB toolbox is used to extract the corners of the checkerboard pattern for each image and solve the perspective endpoint problem with these data points and the known dimensions of the checkerboard squares. This calibration provides us with the intrinsic parameters and distortion coefficients for the C270 webcam. We use the HAMPI module to detect AR tags generated using Hamming code. The HAMPI module provides a function for generating AR tags with a desired ID and size, and this allows us to create a unique tag for each object in the robot workspace. The HAMPI module function, detectMarkers, returns all tags found within a video frame. Found tags are returned as a Hamming marker object, which contains the ID, contour, and size of the detected tag. On raw unprocessed video at 20 frames per second, the HAMPI module results in a marker detection rate, or MDR, of about 9.79 markers per second for a randomly moving marker with random shadows cast across it. MDR is improved by pre-processing the video frames before attempting to detect if any tags are present using HAMPI. We process frames by first grayscaling and then thresholding the pixels to either pure black or pure white based on a percent pixel strength decision boundary. The highest MDR is achieved for the range of 30% to 40% pixel strength as our thresholding decision boundary, and 40% is chosen to make it slightly harder to white out pixels due to the bright lighting conditions of the lab space. Finally, a slight Gaussian blur is added to each frame to soften the image a little. For the pre-processed video at 20 frames per second, MDR using HAMPI is increased to 14.1 markers per second for a randomly moving marker with random shadows cast across it, a 44% increase as compared to the unprocessed video. In order to touch an object marked with a tag, we need to determine the position of the tag with respect to the robot frame. We can solve for this vector by considering the diagram on this slide. We can see that the position of the tag in the robot frame, POA, is equal to the vector addition of POT, the position of the end effector in the robot frame, PCT, the position of the end effector in the camera frame, and PCA, the position of the tag in the camera frame. We determine PCA using OpenCV's solvePNP function. This function takes 4 arguments, 2 of which are the intrinsic parameters and distortion coefficients of the C270 webcam calculated from calibration. The 2 other arguments are the 2D to 3D correspondences for a detected tag. The 2D points are defined by the contour returned by the HAMPI module when a tag is detected, and the 3D points are free to be defined by the user. We define the origin of a detected tag frame to be at the center of the tag and determine the tag contour in millimeters using the actual size of our tags, which is 25 millimeters by 25 millimeters. By this definition, the solvePNP function returns the pose of a detected tag with respect to the camera frame. We determine PCT by manually moving the robot arm so that its end effector touches a tag in which PCA has been calculated. Querying the robot position at the beginning and end of this manual movement gives us PTA, the vector connecting the end effector of the robot to the detected tag. We then use vector addition to solve for PCT. Since the camera and end effector are attached to a rigid body, PCT remains a constant. For each tag that is detected and PCA is determined, we can calculate PTA in the robot frame using vector addition. The position of a detected tag in the robot frame is therefore the current position of the robot end effector plus PTA. The robot simply moves to this new position in order to interact with any detected tags.
All right, so we can get started here, and I'm putting the robot onto the circle here to make sure that this base is aligned correctly. I turn it on, and we're going to go ahead and run our behavioral code. So it's starting up the serial interface, that runs on a separate thread, and it's initializing the camera, which is also on a separate thread. So there you go, you see it pop up there, and it already sees the tag. If I put in multiple tags, it should detect them just fine. Very nice. All right. So let's look at the behaviors we have. We have top view, get data, touch, track, grab, place, all sorts of things. Let's go ahead and do grab ducky. That's a pretty basic one. So then come over here, and it's going to try and grab the ducky and bring it around. And that worked pretty good. So we're going to hit reset. It's going to drop the ducky. right onto the tag, nice. I'll put it back. And now let's do something a bit more complicated, search and place. And we get a choice of which object to place the ducky on. So to do that, I actually have to look up, when I initialized this camera, I had all these tags printed out. These are what's registered with the camera. So the ducky bot has a certain tag, and it is this guy right here. So on the back of these tags, we've actually marked the number. Of course, I could just put it in front of the camera, and it'll show me it. But that's a match with the ducky bot. So let's do that. So go back down here, place it onto the ducky bot. We're going to clean the workspace, which means it's going to clean any unknown tags. And we're going to do no path planning, no obstacles. So let's move this out. Maybe let's say down the path a little bit. So there it is in view. And then let's put some obstacles. So there's 2 obstacles there. So let's begin. And it's immediately found trash. It's going to come over and hand it to me. Kind of nice. And it's going to find another one. There's one hidden right underneath it. It's going to bring it around. And it's going to keep searching around until it finds the ducky bot. And I had it pretty close in here. It's going to come over here. It's going to find it. Pick it up. It's going to place it right on. And since it's finished its main objective, it's going to go back into its default position and wait for more commands. And in this demo, we have Peter holding up the tag. And he's raised it up a little bit, so the z-axis is not as low as it used to be. What we're going to do is do some tests and show it's still working. So if we do touch, see it comes down, and I can reset that. And even if he moves it, I touch again, it's fine. Now I'm going to do something else. I'm going to actually place a ducky on there. So it's going to bring it around. I'm going to grab it, come over to his finger, and it might be a little bit of a rocky landing, but yeah, that's fine. It works pretty good. And then if we hit quit, it quits cleanly, and it's all good. All right, so we're going to do another test here. And what we're going to do is we're going to place it into a behavior. This is the tracking behavior. So we're going to say track the ducky bot, and it's going to go into a search mode. So it's looking around, and if it'll just do it forever until it finds the object. If I wanted to stop it, I could spam it with commands. That'll break that behavior. Notice the base is no longer rotating until it's reset, so it's responsive once again. So let me go back into track. And this time, while searching, we're going to have the tag come out. And it's found it. And notice that it's tracking right above it. And if we move it slightly, it follows it. And you can raise it up. It works. Maybe bring it down. Notice that it told us there's no solution for certain coordinates. So it raises above a certain point. If you go too high, it'll go beyond its bound. So it tells us it can't track that high. All right, and then what I'm going to do now is I'm going to exit out of this, and I'm going to touch that tag. So touch down. Oops. Is it in a bad position? It's probably too far away. All right, let's bring it a little closer. Touch 2. There we go. So it's a little difficult at certain bounds. The Dobot can't reach out too far. You notice in here, it actually said there's no solution for certain coordinates. The x value is far too large. So it's out in this direction too much for it to reach out that far. And then if I do this again, see if it works. Touch 2, and there we go. Reset. And there's a little bit of movement right now. It's kind of flickering, so it's not 100% accurate on that, but it's pretty good. Let me click quit. All done. All right, so we're going to start another test here. The robot is starting up. Just booted it. It's all good. The camera feed is going to come online. And good. All right. So what we're going to do now is we're going to do some search and place behavior, but this time we're going to do path planning. So clean the workspace, avoid obstacles, and let's see it go. So as you can see, the giant obstacle in the room is the plank of wood here, and hopefully it'll avoid it. I believe it will. So let's take a look. it's choosing a path along a probabilistic roadmap to avoid the plank. And since it's always in that same position, it's pretty easy for us to code that in. It looks like it avoided it pretty good. So that was garbage. It's going to go on the return path, also trying to avoid the obstacle. And the next tag it's going to see is the ducky bot. So the ducky bot, it's actually going to come over here and try and grab the ducky, while of course still trying to avoid the obstacle. So everything should be set. Let's see it work. It's always kind of fun when you can see the ducky in the actual video capture. Now it's returning it back. It's looking good. You'll probably see the tag too on its return path. So let's see if we get a shot of that. If you look at the bottom right-hand corner, you see the tag there. And there it is. It got registered. But usually it gets blocked off like that at some point. And it dropped off. This is a very good test. And then we tell to power down. So quit. All right, so we're going to do some more tests here to show the repeatability of our experiment. So we're just going to do a lot of behaviors one after another. So let's go ahead and do a stack test with the 3 tags that are in view. I'm just going to grab the tags and just put them on top of each other. Nothing too special. It looked like that worked pretty good. All right, so let's play around with these tags a little more. So we have some DuckyBot ones. We have garbage ones. I'll take these 3, stack them up. So these will be all garbage. And this one here is the DuckyBot. So I'll put the DuckyBot over here. Let's put it right there. All right. So let's see if that works. So let's do a search in place. Look for the DuckyBot. We're going to clean up for garbage. All right. And I found the first one. It's going to bring it over to me. All right. Pretty good. Found another piece of garbage, because there's one directly underneath. I can already tell it's going to detect the 3rd one, so that's pretty good. Very nice. And it's going to continue its search looking for that ducky bot. And it found it the second it came to frame, which is very good. It's coming down to get the ducky. Perfect grab. Very nice. It's going to land it straight down. So that test went pretty good. All right, let's do some more. Let's do grab ducky. So I placed it back here. I think it's roughly right. Grab ducky. It's coming around, and it looked like it got it. So that's pretty good. So set. Very good. And then let's see if we can do a touch test. So touch. All right, very good. Set. All right, let's go and grab that ducky one more time. Very good. Awesome. So yeah, these experiments are one after another, not too much of a hassle. Let's try that again with the stack. So here's our garbage stack, the ducky, all that stuff. Okay. So basically the same test as before, but can it do it again without any errors? Here for place, ducky, clean, and no. So I found the first garbage piece, it's coming around, dropping it off. You've already seen this before. Let's go back around. So getting the tags is very consistent. The one thing that requires the most accuracy, though, is getting the ducky. If that's off by even a millimeter, it can be a problem. So that's why we try to make sure this is in a nice station. Coming down, and then it got it. Very good. Yeah. There is a demonstration of a lot of tests back to back. And then you can quit. And all good. Alrighty. one of the biggest hurdles we ran into during this project was the environment we were operating in. So we would have the Dobot perform a behavior, and sometimes it would fail. For example, grabbing the ducky, perhaps it wouldn't make contact, and then it would just miss the ducky. If that would happen, we'd have to ask ourselves, okay, do we have an issue with our code, or do we have an issue with the environment slightly changing? Maybe the ducky wasn't in the exact right position. So you'll see over here that we have all these values that are pretty specific. These are in millimeters. So if any of these are off by even just a little bit, it could cause serious problems. For example, the camera offset, which is relative to the end effector, could be not, or the ducky position on the table could be slightly different, or even if the ducky itself was warped, then that could change where we need the end effector to touch, also with the garbage can position. So how do we fix this? Well, the way we had handled this was we structured a platform in which we could slide the Dobot into so that we knew the XY positions would be relatively the same every time we ran an experiment. Then we also drew a circle onto the table where we would bring down the end effector to touch, and that's how we knew that the angles were roughly the same, especially the base. That would be the hardest one for us to make sure was exactly correct. So with that all done, we handled most of that, but there were still more hurdles. After that, we started running into issues where we found out our code was not compatible with each other. So we all had different platforms running. Although Python, which is the basis for all of our code, is multi-platform, the modules we're using were not all the same. We had OpenCV, which is for the image processing, and that there's a latest stable version that we were using. Dylan was using the latest beta, and we found some advantages with the beta that we decided to keep it in, but we had to change some of the syntax, otherwise it just crashes. So we put in cases for that. Even with the markers, same issue. There's different syntax for that. So we had to put in all these cases where, okay, well, if you're running this, perform these steps, or otherwise do this. So that was solved. Another thing that we had was, all right, we have multiple operating systems. So we have Windows, we have Mac, and we have Linux. Windows originally did not work. We were using PyDobot, and PyDobot creates a serial connection with a Dobot, and it was not working. We eventually solved it. We thought it wasn't going to be solved, but we eventually found that the arguments it was sending far more than these. Originally there was, I believe, 5 or 6, and PySerial, which is what PyDobot connects into, has default arguments, and the ones that it was choosing by default were far more reliable than the ones it was choosing. So we removed some arguments, found it to start working with Windows, tried it on Linux, and it still worked. So we were able to get this to work on all operating systems, so it was also working on Mac, and that was a big help. Unfortunately, we only fixed it far later in the project than we had hoped, but it's better done than never. So the last issue we ran into was with our camera code. Our camera code crashed all the time. Every time you exited, it would crash. So what was happening was a race condition. It was gathering data here, and then it would release. It would take the capture, and it would terminate. But if it terminates here, while it's still capturing data, then it's going to crash. It's going to try and reference something that no longer exists. So we had modified this, and so it knew that, okay, if you're stopping, close down, finish your processing, wait a bit in here, 1 second, which if you're capturing 20 frames a second, that's plenty of time, then destroy the feed and release the video capture. Once we did that, everything was fine. And now it exits cleanly. It's great. But for the vast majority of the project, it was not. So we solved all our major hurdles. The only thing that really can't be solved completely is the fact that you'll have these positions that are fixed, and you need to make sure that they stay the same. So if the camera gets bumped by something, this might need to be recalibrated, which can be done with touch tests. And then these here, you can also check by doing grab ducky commands. If it's slightly off, either change its value or change where the ducky is. So there are ways to mitigate it, but it's still a hassle. It's not completely automatic, and it's not some other bug fix like we found in other places. That's just one-time fix forever. So yeah, that was the major hurdles.